Okay, so now page number 31. So we have here an exercise number 20 where xn is given by n squared over n plus 1 minus n cubed over n squared plus 1. In this case, you see that the limit of the first term is infinity, and also the second term is also infinity. So we have the indeterminate form like infinity minus infinity. So as in the previous situations, we have to rearrange our nth term of our sequence. So we go to the common denominator, and we have that x sub n is n squared minus n cubed over n cubed plus n squared plus n plus 1. So, as usually, I repeat, we have to divide the numerator and denominator by just term. In this case, it is n cubed. So we have that the limit of our sequence is 1 over n minus 1 in the numerator over 1 plus 1 over n plus 1 over n squared plus 1 over n cubed. So now we can make use of our limit theorem because we know the limit of our numerator and we know the limit of our denominator. So the limit of our numerator is minus 1 because 1 over n goes to 0. And similarly, we have that the limit of our denominator is 1. So the limit of our sequence is minus 1. Is it clear?
Yes, it's clear.
It's clear. Very good. So now, we have, so now we turn the page and let's consider exercise number 21. So in this case, we have that x sub n is nth root of 8 minus 1 over nth root of 16 minus 1. So in this case, you see, I hope you know that due to exercise number 5, the nth root of a is positive in this case, the nth root of a goes to 1 as n goes to infinity. So if we consider our sequence x sub n, we see that the numerator goes to 0 as n goes to infinity, and also the denominator goes to 0 as n goes to infinity. So we have an indeterminate form 0 over 0. How to work with? You will see that in order to rearrange such fractions, we make use of the formulas like, you see the formula a cubed minus b cubed is a minus b multiplied by a square plus ab plus b square. And as for a to the power 4 minus b to the power 4, we can write that it will be a minus b multiplied by a plus b multiplied by a square plus b square. Is it clear?
Yes, it was a little bit confusing at first because we needed to change the theorem a little bit, but now after like you described it right now, it makes sense.
You see, in this exercise, in a lot of exercises, the dangerous term, you see, is the term a minus b. In this case, if you have nth term of 8 minus 1, so the problem, we have a problem with the term nth root of a minus 1. And in this case, it will be the same thing for the denominator. So using this formulas with a, nth root of a and b equals 1, we write, as for the numerator, it will be the product of nth root of 2 minus 1 multiplied by the nth root of 4 plus nth root of 2 plus 1. And as for the denominator, we have also nth root of 2 minus 1 multiplied by nth root of 2 plus 1 multiplied by nth root of 4 plus 1. So we can simplify this fraction in order to have in the numerator, evidently, nth root of 4 plus nth root of 2 plus 1 over nth root of 2 plus 1 multiplied by nth root of 4 plus 1. So, due to this exercise number 5, we know that nth root of 4 in the limit as n goes to infinity is 1. Nth root of 2 as n goes to infinity is also 1. So in the numerator we have 3. The limit of the numerator is 3. The same thing in the denominator. In the denominator we have that the limit of denominator is 2, because the nth root of 2 goes to 1 and nth root of 4 goes to 1 also. So in the denominator we have 4. Then the limit of our sequence will be 3 over 4. Is it clear?
Yes, it's very clear now.
Very clear. Thank you. So now we turn the page, and let us prove some rather useful result, which is given as auxiliary lemma, page 33. So I suppose that my sequence x sub n is non-negative for any n. Okay. Moreover, the formula 4.1 is valid. That is, the limit of xn as n goes to infinity is a. Then if I take this sequence, square root of xn, the limit of this sequence will be square root of a. So it is, I formulated this result as a lemma. Okay. So now let's go to the proof of the lemma. First of all, due to the definition of the limit, you see in 4.1 we have the limit of a sequence x sub n is a. So I write the definition of my limit. For each epsilon positive, there exists capital K, which depends on epsilon, such that for any n greater than this capital K, we have that the absolute value of xn minus a is less than epsilon multiplied by a constant square root of a. I agree with this formulation.
Yes, I agree with it.
So no problems, because we have for any epsilon that the absolute value between the x sub n and a is small. But if I say that it will be less than epsilon over 2 over 3 over 4, it will be the same thing. I can also say that it will be less than epsilon multiplied by 5 or 3 or 7.2. It will be the same thing, because I can obtain that the absolute value between x sub n and a is small, because the smallness depends on epsilon. So it is, I use here, you see, I use here this constant square root of a only for the sake of simplicity. You see, it will be,
Yeah, I see it.
it's clear. So now, let us estimate. What do we want to estimate? Due to the definition of the limit, I want to estimate the absolute value between square root of xn and square root of a. So in this case, as usually, as for the differences, we make use of the formula. A square minus b square is a minus b multiplied by a plus b. So we can write that the square root of xn minus square root of a multiplied by square root of xn plus square root of a divided by square root of xn plus a. You see here, I multiply the numerator of my fraction x square root of xn minus square root of a divided by 1. I multiply this fraction by the term square root of xn plus square root of a, and I multiply the numerator and the denominator. Okay? In order to have in the numerator, I have that the product of xn, square root of xn minus square root of a, and square root of xn plus square root of a is xn minus a. Due to this formula, a plus b multiplied by a minus b is a square minus b square. Is it clear?
Yeah, I understand it.
So as for the denominator, we have in the denominator we have square root of x sub n plus square root of a. But you see, as for the denominator, here we have two positive numbers because square root of xn is greater than 0. And the limit of the sequence A is also non-negative. So I can write that square root of xn plus square root of a is greater than square root of a. Okay? So,
Yes.
yes. So we will have that this absolute value is less than the absolute value of xn minus a divided by the square root of a. Evidently, here we have to assume that a is different from 0. Is different from 0. Okay? Then we turn the page and what do we have? We have that from our definition of the limit 4.3, we have that the absolute value of square root of x sub n minus square root of a is less than epsilon. But in the definition of the limit, for any epsilon, we have some cut of k, such that you can see this formula 4.3. So in this case, we have this cut of k such that for any n greater than this capital K, you have that the absolute value between square root of xn and square root of a is less than epsilon. Then you see, due to the general definition of the limit, we can say that the formula 4.2 is valid. So a very useful result in view of the following remark, because here we have proved this result in the case of the square root. But if we take p another or some natural number p, so the limit as n goes to infinity of piece root of xn will be the piece root of a. So in this case, you are dealing with the roots in a very simple way. In a very simple way, if you see the corresponding root, and if you know that your sequence x sub n goes to a limit a, then you can use either the formula 4.2, either the formula 4.4. Now we try to discuss the application of this fact. Let's turn the page and let's consider the exercise number 23. In this case, you have we want to find the limit as usually of x sub n, and x sub n is the square root of n squared plus 1 minus square root of n squared minus 1. So in this case, you see the first term goes to infinity, the second term goes to infinity. So we have an indeterminate form infinity minus infinity. So we cannot use our limit theorem in this case directly, and we have to rearrange our nth term in the following way. So as in the proof of this lemma, we make use of the formula a minus b multiplied by a plus b is a square minus b square. So we rewrite our nth term in the following way. So we multiply our nth term by n square root of n squared plus 1 plus square root of n squared minus 1, and we divide by the same value, that is square root of n squared plus 1 plus n squared minus 1. You see, no problems. So in the numerator of this fraction, due to this formula 4.5, we have that the numerator of our fraction is 2. And the denominator of our fraction is square root of n squared plus 1 plus square root of n squared minus 1. So in this case, the square root of, for example, n squared plus 1 is something like n. So we have a fraction which is equivalent to the fraction 2 over n plus n, and the limit of this fraction will be 0. Is it clear?
Yeah, it's clear.
Clear. So in other words, if you want, if you have that your xn it is greater than 0, yes, and from the other hand, it can be estimated by 2 over n from this inequality, excuse me, because in the denominator you have a sum of 2 positive numbers. So xn is less than 2 over square root of n squared plus 1. Is it clear?
Yes, this is clear for
So,
me.
moreover, in this case, it will be less than 2 over n. We forget about 1.
Yeah, I understood. Yeah, I see it.
So in this case, you see, what do we have? We have, if you want, we can use the two policemen theorem. You have the left-hand side a constant sequence 0, 0, 0, which goes to 0 evidently, and on the right-hand side you have a sequence 2 over n, which also goes to 0. So your sequence x sub n goes to 0. So the limit is 0. Is it clear?
Yeah, I understood it.
Yes, it's clear.
It's clear. Good. Good. So now, page 36. It is, if you want, the same kind of exercise. In this case, you have also the undeterminate form like infinity minus infinity. But xn is given by the formula square root of n plus a1 multiplied by n plus a2 and this square root and minus n. So we have to use the same formula number 5.5. So we multiply our x sub n by the square root of n plus a1, n plus a2 plus n. And we have to divide by the same thing. So in the numerator, if we multiply two terms, and we have to use this formula, a minus b multiplied by a plus b. So it will be a square minus b square. So we will have the following, that in the numerator we have a1 plus a2 multiplied by n plus the product a1, a2. And in the denominator, I write it like this, n multiplied by the bracket square root of 1 plus a1 over n multiplied by 1 plus a2 over n, and all this plus 1. Is it clear here?
Yes,
Yeah, it's clear.
Professor.
Yes, very good. So if I divide now the numerator and the denominator of my fraction by n, I will have in the numerator a1 plus a2, so a constant, plus something like a1, a2 over n. This sequence goes to 0. And in the denominator, we have the square root of a product 1 plus a1 over n and 1 plus a2 over n. So we know that this sequence 1 plus a1 over n, for example, goes to 1. So due to our lemma, we know that the limit of the square root of this sequence is the square root of the limit. So it will be the square root of 1, so it will be 1. Then we have the same thing for the second term, 1 plus a2 over n. So the limit of this term will be also 1. So the limit of our sequence x sub n is the limit of my numerator, which is a1 plus a2, and divided by 1 plus 1, that is 2. So the limit of the sequence will be a1 plus a2 over 2. Is it clear?
Yes, it's clear.
Yes.
Good. Good. Very good. So another example. You turn the page. It will be the page 37. So we have, pardon, just a moment. So we have the sequence which is given by x sub n is 1 over n multiplied by square root of n square minus 1 minus n. So in this case, we have an indeterminable form like 0 by 0. Why? Because if I want to write my nth term in the form, in the numerator 1 over n, and in the denominator square root of n square minus 1 minus n, then the limit of my numerator is 0, and the limit of my denominator is also 0. So we have the form like 0 over 0. And in this case, we make use, as usually, of this trick. So we multiply our nth term by square root of n square minus 1 plus n, and divide by the same term. Then in the numerator we have that it will be n square minus 1 plus n over n, and with the sign minus in front of our fraction. Because in the denominator we have n square minus 1 minus n square, it will be minus 1. So now dividing the numerator by n, we will have minus square root of 1 minus 1 over n square minus 1. So from our lemma, we know the limit of the square root. It will be minus 1, minus 1, minus 1. So the limit, the final result is minus 2. Is it clear?
Yes, it is, Professor.
Clear.
Yeah, it is.
Clear. You say it's clear.
Yeah, it's clear.
Okay, very good. So now, the last exercise in my planning will be the following, and then we will discuss briefly some examples without a special file. So I will ask some questions and we will try to find the answer. So the last exercise, exercise number 26, it is a limit to remember. It is an important limit which you have to know. So in this case, we have that the nth root of n goes to 1 as n goes to infinity. So in this case, you see, what do we have? We want to make use of the binomial theorem. So the first step is to represent our n in the following form. I write that n is 1 plus nth root of n minus 1 to the power n. Is it clear?
Yeah, it's clear.
Yes.
So, first of all, what is important that the nth root, nth root of n is greater than 1. So we have 1 plus something positive. You see? Now we make use of the binomial theorem and we can write that it will be 1 plus n multiplied by nth root of n minus 1 plus n multiplied by n minus 1 over 2 multiplied by nth root of n minus 1 square and so on plus nth root of n minus 1 to the power n. Then you see in this relation on the right hand side of this equality, all the terms are positive. Then if I take here only the third term on the right hand side of my equality, I will have that n is greater than n multiplied by n minus 1 over 2 multiplied by nth root of n minus 1 square. Is it clear for you?
Yeah, it's clear.
Clear. So you see, in this case, if you want, you can take the third term, for example, but it is not necessary. It is enough to take the second one. You see? Then, from this inequality, we will have that the square root of the nth root, nth root of n minus 1 is less than square root of 2 over n minus 1. So, as usually, we have two ways to treat this inequality. The first way is to use the definition of the limit. You see, I can use the definition of the limit knowing that the limit of the square root of 2 over n minus 1 is 0. And then for any epsilon, I can find the cutoff capital K depending on epsilon, so on. But also, also. I underline this. We can also use the two policemen theorem, because on the left-hand side is, we know that the square or the nth root of n minus 1 is positive. So we have a sequence, a constant sequence 0, which goes to 0. And on the right-hand side, you have another sequence which goes to 0. So you have that really the limit of nth root of n is 1. Is 1, as it was claimed in the formula 4.6. Is it clear?
Yes, it's clear.
So, as for
Yes.
as for this file, it's finished. So we have time. We have time to. I will put you maybe 1 or 2 questions in order to discuss. Maybe it will be. I hope it will be useful for you. So you have. I hope you have a pen or a pencil and a sheet of paper. Mhm.
Okay, I have my
Very-
paper and pen.
So, let's take your, please write that your sequence Z sub n is given by X sub n over Y sub n. Okay,
X sub n over Y sub n.
very good. Now, as for X sub n, I say that the limit of X sub n is 0.
Okay.
Moreover, the limit of Y sub n is also 0, but Y sub n is different from 0, evidently. Y sub n is
Mhm.
different from 0, but the limit of this sequence is 0. So, give me please an example such that the limit of the sequence Z sub n as n goes to infinity is 0. So you have, I repeat, you have two sequences. So Z sub n is x sub n over y sub n. Okay?
Mhm.
The limit of x sub n is 0. The limit of y sub n is also 0, but y sub n is different from 0 for any n natural. Okay? So please give me an example such that the limit of my sequence z sub n is 0. What do you think about?
Well, for X sub n, maybe I can put something like um it needs to be the limit will equal 0. Let me see. Maybe I can put like no, no. Wouldn't make sense. It,
You
I
can
mean,
you can sing. You can sing for a moment. I'm waiting. We have time.
okay. Because what I'm thinking is that, X sub n and Y sub n need to be kind of similar in a way, because I mean, even though Y sub n does not, it's different from 0. it's still those two sequences needs to be very similar.
Very
I
similar.
suppose.
But not, you see, the next question, you will see the next question. But for the moment, you see, I want this result. So an example when z sub n has a limit which is 0.
Okay, let me just give me a second to think about it. Um, I mean, while I think about it, maybe there's somebody else in class that maybe has an idea already. I'm not sure. Maybe for an example, I mean, I'm not sure. Let me see. So it could be something like x, oh no, n plus 2, maybe over n squared minus 1.
So xn is, can you define this sequence? X sub n, what's this?
X sub n, I would put it as x plus 2, or n plus 2, I'm sorry.
So n plus 2, this sequence goes to infinity. Eric.
No, yeah, we needed to do 0. Yeah. Um, let me. So, I'm having a little bit of difficulty trying to figure out a sequence that makes it, because every time I write one, it goes to infinity. I mean, because maybe it could be something like, n plus. Let me see.
So proposition for the moment. If I take x sub n like 1 over n squared.
1 over n squared.
So now you have to find y sub n such that the limit of z sub n is 0.
Where 1 over n squared, correct?
Yes, xn is 1 over n squared.
انا مهتم بس انا
So,
Because when, for example, Professor, on the example that you provided, which is 1 divided by n squared, I mean, what which I understood is that the limit on that one would be kind of infinitely, well, infinity goes smaller, correct?
yes, so y sub n will be,
Y sub n would have to be the opposite of that. So it would be n squared, or
no. You have
No.
z. You see, you have z. The limit of your y sub n is also 0. Okay?
yeah. But I mean, it can't be the same equation. It needs to be a little bit different because it needs to.
So, Eric,
Yeah.
now, I think I will give you 3 questions. You will think about, and we will discuss this next time. Okay? Next Friday.
Yeah.
Okay? So, the first question is,
لوين
I say that you have z
ما عنديش
sub n is x sub n over y sub n. Okay? And the first situation, I want to have an example when the limit of z sub n is 0. It's the first situation. Okay? The second situation, I want to have an example when the limit of z sub n is plus infinity. Okay? You understand?
Yes, for the first and second one, yes.
The third example, I want to have an example when the limit of z sub n is, for example, 6. You see? Okay?
Yes, I see it. Okay.
But it is now the last example. Do you know
Okay.
an example of a sequence which does not converge, which does not have a limit?
طيب وش يعرف قديش
let me see.
Good. At least, if you take a sequence -1 to the power n, you see,
جدين خام على السنتر
it is not a convergent sequence.
بدي يطلع
Not a convergent.
مش معرفة
Yeah, kind of like.
So the last question was this exercise exactly for you, because we will discuss this next time, and I think it will be useful for all the people. So the last example, I want to have an example when the limit of this sequence z sub n does not exist. You understand?
Yeah.
So you have, I repeat, you have that the limit of xn is 0, the limit of yn
Mhm.
is also 0, but yn is different from 0. Only the limit is 0, you see? And we consider with you the sequence
Mhm.
z sub n, which is x sub n over y sub n. Okay? And I want to see 4 examples. The first one, the limit of z sub n is 0.
Mhm.
The second example, when the limit of z sub n is plus infinity. The third example, when the limit of z sub n is 6, for example. If you like 7, it can be 7. And finally, the fourth example is the limit of z sub n does not exist.
انت بتقول اصنع تعبان يعني.
Okay, got it.
So next time, next Friday, we will discuss this with you. If you want personally, if you want with all other with all other colleagues. You see? So you have to think about, because this kind of examples is very important in order to understand the limit theory. You see?
Yeah, I see it. Yeah.
Okay. So
Mhm.
thank you for this work, and see you next Friday. If you want to contact me during the week, we can speak by Skype if you want. Okay?
Okay, thank you,
Okay, sounds
Professor.
perfect. Yeah.
Ciao, ciao.
Ciao.